Okay, so hello everyone who are watching this on YouTube. Let's take a look at chapter 1, get a little bit further into the chapter and get on to the more important stuff of metric conversions shortly. So, oh, hello. Yes. What is it? What do you need? Excuse me.
You.
Oh, that's great. But can you watch some TV for a little bit with your...
I need you to help
Uh-huh.
somebody
Uh-huh.
get somebody.
Can I help you later? Because I'm talking to all these people. Okay? Excuse me 1 second. Can I come and help you later? What is it you need?
I want you to help me with my baby teddy bear.
All right. Apparently a teddy bear needed to be tucked in and kissed goodnight. Okay. 4-year-old problems. Right. Sorry about that. Let's see. So we were looking at these equations, chemical reactions for our elements and compounds. And we had said that there should be balance over the stretch of the reaction. All these chemicals on the left, these are the starting ingredients. These are the chemicals which are going to be used up in the course of the reaction. And then the arrow is representing the change which is going to take place, the inferred change. And then everything on the right-hand side is everything that comes out of the reaction, all the chemicals which are produced. So the chemicals that we're using are what we sometimes refer to as the reactants. And the chemicals on the right are what we call the products of the reaction. Apologies for my horrible handwriting. Looks like I'm on horseback with the hiccups while involved in a ninja sword fight as I try and write. Anyway, so looking at these questions here, hydrogen gas can be best described as, well, we'll look for the hydrogen. There it is there. It's on the right-hand side, so it can be best described as a product of the reaction. All the stuff that goes in, all the stuff that comes out. How much calcium does the reaction use? Well, it doesn't tell us, of course, but we've got this idea that all the chemical that goes into the reaction must be equal to all the chemical that comes out of the reaction. So total mass in should equal total mass out. It's what we call the conservation of mass over the course of a reaction. I almost said conversation and I couldn't think of the right word there, but never mind. So everything that goes in by mass must come out by mass. And so when we look at the total mass coming out, 110.9 plus the 2, that's a total of 112.9 grams. And we know that we are accounting here for, from the hydrochloric acid, it accounts for 72.9 grams. So we must have that total mass going in, and 72.9 grams of it is the hydrochloric acid. The difference would be the mass of calcium, which would be the 40 grams. How much calcium is there when the reaction is finished? Well, calcium is part of one of our products, calcium chloride, but different chemical formula means it's a different chemical. This is not calcium anymore, and it doesn't react the way calcium would, just because it contains calcium. Just like different chemicals or different foods with sugar are not going to taste or feel the same in your mouth. So there's 0 calcium by the end of it. We've got 110.9 grams of calcium chloride if the reaction works perfectly, but that's not the same thing as calcium. How much calcium chloride is there when the reaction is finished? Well, that is, of course, one of our products. So we're hoping for 110.9 grams of that. Again, these are idealized figures. If everything works perfectly, we'll get these exact amounts to come out. And we'll look later in the semester at examples where maybe we get less than that perfect amount. If the reaction produced 6 grams of hydrogen, how much hydrochloric acid and calcium would be used for it? So 6 grams of hydrogen is inferred. According to our balanced equation, normally there's only 2 grams. Now this is just like cooking. If we want 6 grams, which is 3 times more, like if we wanted to make 3 times as many cupcakes, we'd have to use 3 times more of the starting ingredients. So it's the exact same philosophy. We know this is 40 grams here. So we need 3 times more of this, 3 times more of this, if we want that to be 3 times more, because it'd be 3 times more calcium chloride. So let's see, 72, let's say 70, 140, 210, 216, 217, 218. I think that's 218.7. But just because I'm paranoid, let me check with a calculator. 72. 218.7. Ooh, on the nose. Whatever you're trying to calculate, always try and use your head first time. Never reach for a calculator unless it's just a safety check. Then of course 120 grams of the calcium being reacted 3 times more, that's easy enough. So any reaction should always be in proportion. If you want to produce double of one of the products, you're going to use double of all the starting ingredients. If you only want to produce half as much, then you use half as much of the starting ingredients. There's that balance for the whole reaction. Name two things you could observe that would suggest the reaction was working. Let me get rid of all this clutter here with all my pork scratchings. Let's see, we start off hydrochloric acid and calcium. So over the course of the reaction, we use up these chemicals, and the calcium is given as a solid. So if the reaction starts, that solid starts to disappear because I haven't left myself enough room here. So that solid calcium would start to disappear in front of your eyes as it gets used up. One of the products, hydrogen gas, is of course a gas. So we would see bubbling or effervescence, as I mentioned on Wednesday. That bubbling could only be from the hydrogen gas product being produced. Sometimes you might see a color change. Maybe if the initial chemical being used is pink or something, as that pink color disappeared, it faded, you could say the chemical is being used up. Or if one of our products had a different color, and this is just made up, calcium chloride is not orange, and calcium is not pink, but if it did have a color, as a new color appeared, you could imply that you're producing more of your product. Okay, let's see. There's a little thing that flashed on my screen there as if I've got some text messages. Are you sure? Can anybody see the notes in front of them?
I can see him.
Okay. Does everybody now see them?
Yes, I can see them.
Okay, and everybody, is there anybody who can't hear me? Give me a no. Somebody just said. I'm terrible with my colors. Somebody said, when cyanide is present, the color blue appears. I just happen to use blue just to make my picture look prettier. So that's an important thing to point out. I'm not suggesting that calcium has that color, if that's what people were perhaps mistakenly thinking. I just like using pretty colors. Certainly there are chemicals that have a color to them, but there's very few. Really the only group of chemicals which have a natural color are really the halogens. Chlorine is a kind of green. Fluorine, I think, is a fluorine. I can't remember. Bromine is a blood red brown. I remember that. Iodine has a purple color, but most of the elements have a complete lack of color. So I'm just trying to be, I guess, make my chemistry look more cheerful. So that's a good thing to point out, though, because that could confuse people otherwise. Okay, so this lecture will be uploaded on YouTube as normal. So if you do have a problem, bear with it and just watch the YouTube video later. But it looks like just about everyone can hear and see me. I can only see one no for that. So for that person, you might have to watch YouTube later. That must be something at your end. Okay. Oh, somebody's now got success. As I mentioned on Wednesday, if you do get kicked out or you're trying to get in, do send me a text, and that usually gives me a little heads up to try and let people back in. Okay. So the real signs of this reaction happening would be that solid would disappear from the reaction flask, and this gas would start bubbling through the solution. The hydrochloric acid and the calcium chloride are both marked as AQ, aqueous, which means that they are water soluble. So even as this is being used up and this calcium chloride is being produced, it would not appear to your eye in the solution because it would just be readily soluble. Okay. Right. So then the last question here at the bottom, what elements and how much of each element appear in our compounds below? Get my pen working again. Why didn't that pen come on? Technology, bah, humbug. So we've got H2O, and it's telling us per unit we've got hydrogen, and the subscripted 2 tells us that there's specifically 2 hydrogens in every unit. The numbers subscripted always infer the element just before it, and we've got 1 oxygen per molecule of water. If there's only 1 atom in the formula, then we don't bother putting a number behind it. Next one, we've got 2 units of carbon dioxide, but per molecule, there's just 1 carbon atom, and now 2 oxygen atoms. H2SO4, which is sulfuric acid, now it's inferring that there's 5 units, 5 molecules, but for each molecule, there's 2 hydrogens, 1 atom of sulfur, and 4 oxygens. And finally, sodium hydrogen carbonate, sodium bicarbonate, often used for antacid tablets. 1 atom of sodium, 1 atom of hydrogen, 1 atom of carbon, and then 3 atoms of oxygen. The only time that a subscript would appear would apply to multiple elements would be if parentheses were being used. Let me quickly show you something like that. So if we had something like calcium hydroxide, which has a formula like that, now that too is doubling everything inside the parentheses. So 2 oxygens and 2 hydrogens in that particular example. So that's the only time that those subscripted numbers apply to more than just the last element that we saw. Okay. Clear that. I think we're now right. Oh, we're almost ready for the metric system. One last little bit to mention is to talk about scientific method itself. So scientists often observe things happening around them, and like say some kind of explosion with a blue flame, and that scientist or worker might have an idea what it is that causes that explosion, but he doesn't know for sure. He's just basing it on his previous experience. Really, it's just a guess, but because we're scientists, we try not to call it a guess. We call it a hypothesis, a reasoning for what's going on based on past experience. And that could be something as simple as this person knows that things that burn with a blue flame often contain copper. You've got your pretty fireworks on the 4th of July. The colors you see are mostly different metal ions burning up. Blue or green for copper, yellow for barium, I believe. I think it's barium. Sometimes you get red for iron. You get variety. So that would be the basis of the idea, the hypothesis, that it was copper. But of course, you have to go into the laboratory and try and reproduce what you've seen. So we're going to try and get some experimental data that backs up this hypothesis. Now, it's either going to work or it's going to fail. More likely, it's going to fail. So you'll go through this kind of loop, maybe 4 or 5 times, maybe 500 times, just tweaking your hypothesis slightly. Maybe you didn't have enough copper for the explosion. Maybe you didn't use the right catalyst. Maybe you didn't heat it hot enough. There's a whole variety of things you can do to try and tweak your recipe and keep going round and round. And eventually, it's either going to work or fail. Excuse me. So you might eventually have to completely disregard or what's the word for it? Reject, there we go, reject your hypothesis. Or you might eventually come to the conclusion that you have enough scientific evidence. If you get to that point where you have laboratory data that seems to back up the hypothesis, we now call it a theory, because it's an idea which is backed up with data. Let's see. And over time, of course, just because you've got this working theory doesn't mean that it might one day still be disproven. And so we'll work with that theory over time, and you'll find scientists constantly, continually trying to break down your theory. Not because they're mean, but because they're hoping that it will stand up to more rigorous testing. Do different environments affect the test? Does a different level of condensation affect the test? All these things. And over time, if this theory still stands the test of time, we might eventually include it as one of our laws of chemistry. An idea that we're now pretty sure of and pretty confident is good. Okay. Right, let me just see what my daughter wants. Otherwise, she'll be back in a couple of minutes. We've been trying to take a 5-minute break anyway. So we'll take a 5-minute break, guys. And when we come back, I might stretch us out to about an extra 15 or 20 minutes, kind of a normal lecture time to finish at about 11:50, just so we get into the metric system a little bit. But take 5 for a bathroom break or grab yourself a drink. My daughter is a master manipulator of me already. She's only 4 years old. I get close to telling her no for something, she just goes deliberately makes that lower lip go crazy. Anyway, enough of my problems. Right, so deadlines always appear on that homepage for Desire to Learn. Keep a look at them. It's always going to be an implication of the last chance or the closing of that thing, other than the exams. As I just said earlier, there's a good chance by Monday I'll announce pushing back all of these deadlines by 24 hours at least. We'll find out on Monday, see how much of the lecture we get through. All right, finally, onto the big piece of the chapter, metric systems. So people around the world have often used different ways of measuring things, different units and different sizes of units. And that can be difficult when you're trying to share information. So a couple of hundred years ago, the French came up with this neat idea of the metric system. And we use it today in science all around the world. So, for example, when measuring distance, a unit for measuring distance is the meter. Let me get my pen working again. So there it is. A base unit for measuring distance is a meter. I think most people have probably seen a meter before. It's probably about the length of your desk at home. I'm probably getting out of shot here. Almost an entire arm length or arm width between your two arms. A meter, it's a little bit more than a yard from what I remember. And that's a nice size of measurement for maybe measuring the dimensions of the room you're in. Maybe 3 or 4 meters high, maybe 10 meters across, or a width of 8 or 9 meters or something. It gives us nice, easy numbers on the eye for measuring distance. However, if we were trying to measure the distance to California, measuring it in meters would give a huge number, thousands, if not millions of units. And so we move to a larger unit when we've got to measure a larger distance. So 1,000 times bigger than a meter is a kilometer. 1,000 meters equals 1 single kilometer. A kilometer is about, it's a little bit less than a mile. It's probably about 0.8, 0.84 of a mile, so that kind of thing. And you quite often see, certainly in Europe, if you're traveling around in mainland Europe, you'll see distances on maps and on road signs measured in kilometers. In Britain, we are sticklers, so we actually still keep the mile when we're not supposed to. It's just one of the many ways we are kind of sadly anti-Europe. But kilometers works for a much larger distance by using a larger unit. And it's a factor of 1,000 between kilometers and a meter. So whatever the value is in meters, to change it into kilometers, you would divide that value by 1,000. If you had a value in kilometers, because there's 1,000 meters to make a kilometer, take that kilometer value and multiply it by 1,000. Basically, if we're starting with the bigger unit, you're going to multiply to get to the other unit. Or if you're starting with a smaller unit, you're going to divide to get to the other unit. But sometimes you might be trying to measure things which are even smaller than a meter. You might be trying to measure the length of someone's nail or a human hair on their body or something. That's going to be a very small value in meters. So 1,000 times smaller than a meter is a millimeter. 1,000 millimeters to make a single meter. So if you had a value for something in meters that was kind of annoyingly small, 0.000 something, it was kind of annoying, you could take that value in meters and multiply it by 1,000 to convert it into the millimeter equivalent. Or if you had a value in millimeters and you wanted to convert it into meters, you would take that value in millimeters and divide by 1,000. If it was a value in millimeters being converted into kilometers, then it's a factor of 1,000 by a factor of 1,000. So you take that value in millimeters and divide it by 1,000,000. The conversion factors multiply up. So 1,000 by 1,000, that's 1,000,000. Then even smaller than a millimeter, down to micrometers, now we're talking about the size of a single cell in the body. You could take a value in millimeters, multiply it by 1,000 to turn it into micrometers, or take a value in micrometers and divide it by 1,000 to convert it into millimeters, or that micrometer value in meters would be divided by 1,000 by 1,000, divided by 1,000,000, or a micrometer value turned into a kilometer value, 1,000 by 1,000 by 1,000, divided by 1,000,000,000. 9 zeros in the conversion. The number of zeros tells you how many times the decimal point in the number moves. The basic thing to remember is if the initial units are the bigger unit, you'll finish with a bigger answer. If the initial units are the smaller units, like say micrometers, then you'll finish up with a smaller answer. And it's really just a case of keeping track of how many times the decimal place is moving. A factor of 1,000 almost every time, except for centimeters. Centimeters are the thing you normally find on one side of your ruler with inches on the other. And so there are 10 millimeters to make up a single centimeter, and there's 100 centimeters to make up a single meter. So it's a factor of 100 between meters and centimeters, and a factor of 10 between millimeters and centimeters. But that still gives us that overall conversion from meters to millimeters of 1,000, because we've got 100 times 10, which is 1,000. So centimeters is the only one which is slightly trickier. It's not the usual factor of 1,000 each time. Okay. And that's as far as I take it. I don't go any higher than kilometers, even though there's gigameters and megameters. And I don't go any smaller than micrometers, like nanometers or picometers, because in medicine, you would never have to measure anything that small or measuring anything that big. It's very unlikely you'll be asked to measure something in kilometers. I mean, that's about giving someone directions to the next hospital. Oh, it's 20 kilometers in that direction. That's not your everyday healthcare work. So although the Gazinski-Smith textbook has a larger range, this is as wide as my range will be for the semester. Sometimes the Gazinski-Smith book just takes it a little bit too far. Get into gigameters, you're starting to measure the distance to the next planet. For the conversion, you can also use the factor label method. You just make sure that whatever your conversion is, like in this case, micrometers, being converted into a meter value, set up your fraction so that the micrometer units will cancel out. 2 micrometers, that's what you're starting with. It's a factor of 1,000,000 between meters and micrometers. The micrometer units cancel out, and we get a conversion to 0.000002 of a meter. Remember, if you're starting with a small unit compared to your final unit, the initial units are small, your final answer will be smaller. The decimal point is moved 1, 2, 3, 4, 5, 6 times to the left. Similarly, with 25 kilometers being converted into meters, kilometer is the larger unit, so your final answer is going to be larger. From kilometers to meters is a factor of 1,000. So you set up your factor label method to cancel out those initial kilometer units. We get a value of 25,000 meters. The 6,500 micrometers converted into millimeters. Again, micrometers are the smaller unit compared to millimeters that you're looking for. So it's going to be a smaller answer by a factor of 1,000. So decimal place is moved 1, 2, 3 times to the left, giving us 6.5 millimeters. Okay. Now the one elephant in the room for doing distance conversions is really inches. Still, even today, we find in hospitals that doctors and nurses still hang on to using inches for measurements. So if you're being told the height of a newborn baby, or even just a child at any age, there's probably a strong likelihood that they would still use inches rather than using centimeters or meters. So for every 1 inch, you have 2.54 centimeters in that 1 inch. So any value in inches can be converted into centimeters by taking that value and multiplying by 2.54. Or if you have a value in centimeters, you can convert it back into inches by taking that value and dividing by 2.54. This is the only example of a non-metric conversion I would expect you to know, because it's so commonly still seen in hospitals. So only inches, that's the only one that's outside the metric system that you would need to know, okay? Let's see, how are we doing for time? I guess I'll stop there. We've gotten a start at least. So Monday for section 1, your Monday lecture is still always going to be online at 11 a.m. Everyone else, the times that you're supposed to meet for lecture, those times will be good. So section 2 will meet on Tuesdays and Thursdays at 6 o'clock for lecture before we go into lab about an hour later. And section 1, we will be live on campus for lecture on Wednesdays and Fridays. And I will still continue to do these Zoom lectures. The time will change a bit because on Wednesdays and Fridays, I'll actually be on campus doing a lecture. But I'll still do some lecture time every single day for people who either miss lecture or for the hybrid people on Wednesday evenings who otherwise don't have access to lecture. These times will start to change a bit, but I will try and pick a consistent time going forward for next week. Okay. Right, guys, thanks for turning up. It was a nice little crowd today, 14 people. And I'll see everybody, or hopefully see people back here Monday morning for that lecture. And I guess it's probably going to be Monday before there's an announcement about whether people are getting back onto campus. I think it's likely, but just listen out on Monday morning or over the weekend. As soon as I know whether the campus is open on Monday, I will let you know on Desire to Learn, okay? Bye, guys. Have a good weekend.